This is an example of solving a problem for a torsional load with a distributed torque. And it also provides an example of testing whether the load causes the bar to fail. So we have an object here that has the following properties. The length is given at 0.1 meter. The radius is given. And the distributed torque, which is called T here, is given at 5 kilonewtons. And note that distributed torque has units of Newton meters per meter, which is the same as newtons. So the ultimate tensile stress of the material is also given, and in this case, numbers weren't available for the ultimate shear stress. So the first thing to solve this problem is that we want to do our critical thinking meta-analysis. So we can ask ourselves, what type of bar is this? Is it uniform, continuously varying, and or is it segmented? We'll also ask, in order to test for failure, which equations do we need? And specifically, which will be most useful? And then finally, we'll ask where we make the cuts to draw the free body diagram. And that will set you up to solve the problem, and then I'll illustrate the solution. So this first question is whether the bar is uniform, segmented, or continuously varying, and it might be more than one of the two. You can pause this video if you want to answer that question yourself. So the answer in this case is there's two segments. There's a region here where there's no load, and this region here where there's a distributed torsion. And so that it is segmented. So that for sure, it is segmented. But within this second segment, it's also continuously varying because the distributed torque will cause an increase as one moves along the bar of the internal torque. So even though that internal torque in this case is uniform, at a uniform density, it's still a distributed load, which creates a continuously varying bar. The next question we ask is which equations will be useful? So in this case, the question we are asking is we wanted to find the extremes of stress on the bar. So that means that the equations that are only necessary to find the angle, the twist angle, are not needed. And that is this one doesn't help and this one doesn't help because those are for the twist angle. So instead, we definitely need to get the equation for stress as a function of internal torque, polar moment of inertia, and R. And that means, of course, we also need the equation for the polar moment of inertia. Now, in this case, we aren't given the internal torque or even a concentrated torque, so we also have to use an equation to help us calculate the resultant torque from the distributed torque, although we'll use a simpler version of that. And then we'll also need then to solve the equilibrium equation to find T of x. So we know these are some steps we'll have to take and equations we'll need to use. The next question we ask is where we are going to cut the bar in order to find internal torque to solve our question about failure. Now, we remember that this means we're trying to find the maximum stress. And to do that, we often do not need to cut the bar everywhere. We just need to cut it in a location where the stress might be maximum. So in some cases, we can use logic to exclude many segments or positions. So in this case, the first thing is to remember that we need to cut within every segment. That means we're not cutting at A, B, and C, and we're not cutting at A because those are segment boundaries. Instead, we cut within the segment. And to be clear on cut, by cut I mean where do we draw the cut and define the internal load, rather than where do we rather than where do we cut to separate the segments. We're referring to making the cut in the diagram, as I'll do in a moment on the next slide. So we cut within segments, and that means that cutting in both segments is fine. But we also might realize that we can save time by recognizing that we're going to start from 0 torque over here at the end where there's no load on the bar. We'll accumulate torque as we go through the distributed torque, reaching the highest amount of torque in segment BC at right as we approach the boundary. But the torque in segment AB is equal to that same value. There's no additional external torque, and so that value will maintain. So it would be fine to cut anywhere in AB or to cut in BC and set the value right here at the end to where we approach that. And so both of these are also correct. And I will choose to use this one, cutting here in AB, because I know the load's maximum there, and that means I don't have to ever even make a cut at an arbitrary x and come up for the equation of how much of that torque I kept. I can just keep all of it, and we'll see that in a moment. So now I'm ready to solve this problem, and I'm going to start, as I said, by making this imaginary cut. When I do that, I can redraw the way this looks with that cut there, where we have this distributed load over this area L over 2, but this time I'm going to replace the distributed load with the resultant torque TR. And TR is going to equal the integral of T, and T is a constant distributed torque, so the integral of that over the length, and the length has that segment has length L over 2, so I just multiply by L over 2, because for a constant load, integration is just multiplication by length. So there's my resultant torque. And now I'm going to define the unknown torque, T of x here, the internal unknown torque. And I define it in the positive direction so that it's facing away from the face of the bar. And we can, by using these double arrows for torque, it looks just like it does for axial load, so the signs are more intuitive to us than if we try to draw them using the right-hand rule with the little curly arrows. So now I have the key parts of my free body diagram, which allows me to quickly conclude that T of x is equal to the resultant torque from the distributed torque, which is TL over 2. Now I'm ready to use the other equations I had identified before. One of them is for the shear stress in the original coordinate system, which is this x theta coordinate system, which is equal to T of x over IP times R. And to find out where this is maximum, we are going to let this thing I have this written over here. It's maximum where R is equal to R naught, and where T of x is equal to TL over 2, what we had there, because that was the maximum value in segment A, and we don't need to calculate it in segment BC. So we plug these in. We say tau x theta is equal to TL over 2, and we have an R naught at the top, and then we realized we also have to get IP, which is pi over 2 R naught to the 4th. And so we'll plug that in over here, and that's on the bottom, so there's a pi on the bottom, a 2 on the top, and then also on the bottom an R naught over 4, which we can then simplify. Those 2's canceled, the R naught cancels with one of those there, and we have TL over pi R naught to the 3rd is our shear stress. This is a good time to check our units. T is in newtons, L is in meters, pi is unitless, and R naught is in meters, so R naught cube is in meters cubed, which is the same as newtons per meter squared, or pascals. Yes, that is what we want for stress. So that so far passes muster on that. And now at this point, we are ready to compare this value to the ultimate stress to test for failure. So I've copied over the values that we were given at the start of this problem, and also what I calculated on the last page was that over the whole bar, all possible locations in this bar, the maximum value of tau x theta was TL over pi R naught cubed. So we'll plug in these values here, and I will spare the math, but I will write them over here, that we have 2,000 newtons times 0.1 meters over 3.14 times 0.01 meters cubed is 10 to the minus 6 meters cubed. And then when we plug all of that in, we have 159 megapascals. So now our job is to compare that state of stress. So the state of stress, the maximum at the point at the location on this bar where it's maximum, is pure shear and 159 megapascals. And the fact that it's pure shear reminds us that sigma x equals 0 and sigma theta equals 0. We were used to seeing sigma x and sigma y, but now we're in the x theta r coordinate system. And the shear stress we're talking about is a unit here on the surface of that. That is what gets sheared when we twist the bar. And so it's the x and theta coordinate system that matters. And so that's why I pointed out those two. But it really doesn't matter what we call them because they're 0 anyway. So in a case of pure shear, we normally would compare this to ultimate shear stress, but in this case, we're only given ultimate tensile stress. There's no ultimate shear stress. This happens sometimes, that these are the only values available for a material because of how the material had been tested. So then the question is, what do we do for this comparison? We can't compare shear stress to ultimate tensile stress. Instead, what we want to compare is tau max would be compared to ultimate shear stress. We don't have that value, so we can't do that. Or sigma 1, we want to ask, is that greater than ultimate tensile stress, or is negative sigma 2 greater than ultimate compressive stress? These are our three questions we're supposed to ask. So these ones are big question marks. We have no way to tell, but we can ask this question. And we can ask it because we can do stress analysis. And when we have this state of stress where we have tau is non-zero, but the sigmas are 0, you remember that R was equal to the square root of tau squared plus half the difference of the two normal stresses, also squared. And so in this case, all of this part here is 0. And so all we have left in that case is that R is the magnitude of tau. And then remember, we also learned, and we could have just known that immediately because we remember that R is the same as tau max, which happens where the normal stresses are equal, which they're equal if they're both 0. But now we remember that sigma 1 is equal to sigma average plus R, and sigma 2 is equal to sigma average minus R. And in this case, sigma average is 0. So these are just equal to plus or minus r, which is to say they're equal to plus that magnitude of tau or minus the magnitude of tau. Oops. So that means that what we're asking is sigma 1, which is equal to the magnitude of tau, which is 159 megapascals, is that greater than UTS, which is equal to, over here, 150 megapascals? And the answer is yes, and that means it does fail. And that's our final answer.